All right, so today we're taking a deep dive into the immune system.
Oh, perfect.
Specifically, we're going to try to clear up the confusion between these two terms that people get mixed up all the time, immunoglobulins and antibodies.
Yeah.
And you send over this really cool article from Assay Genie that breaks down the differences.
Yeah, definitely.
So hopefully by the end of this, we'll all be on the same page.
Yeah, there's a lot of overlap between the two.
Right.
And I think it's understandable why people get confused.
Yeah.
But when you really get down to the nitty-gritty of how our bodies fight off all these, nasty little bugs,
Right.
it's important to understand the distinction between the two.
Yeah. Okay, so let's try to avoid the jargon for a second.
Okay.
And maybe start with like a simple analogy.
Okay.
I always hear people compare this to a lock and key.
Right?
Is that a good way to think about it?
Yeah, I think that's a great analogy.
Okay.
So imagine, let's say a virus is like a key.
Okay.
It's got a very specific shape, right? Right. And that shape allows it to do its nasty work. Now, the antibody is like a lock that's perfectly designed to fit that unique key.
Gotcha.
So once the antibody binds to the virus, it's basically neutralized.
Okay.
It can't do its thing anymore.
So it's like the antibodies are like the specialized weapons then.
Exactly.
That our body creates
Yeah.
to target these specific invaders.
Exactly.
Yeah.
And what makes this even more interesting is that antibodies actually belong to a larger family of molecules called immunoglobulins.
Right. Immunoglobulins.
Yeah.
So are those like the big umbrella term?
You can think of it that way.
Okay.
Like, you've got your army with all its different soldiers and divisions.
Right.
Antibodies are like the frontline soldiers
Okay.
directly engaging the enemy.
Okay, so they're like a subset of immunoglobulins.
Exactly.
Gotcha.
So not every immunoglobulin is an antibody,
Okay.
but all antibodies are immunoglobulin.
Okay, so there are other types of immunoglobulins
Yes.
that aren't directly involved in that.
That's right.
Lock and key, attack and destroy.
Yeah, so it's not just about attack and destroy.
Right.
There's a lot of other things going on.
So there's like communication, signaling,
Exactly.
regulating the response.
Yeah, it's like a complex network,
Right. So it's more nuanced than just like
Much more nuanced.
attack, attack, attack.
Right, exactly.
Okay, so the article really drives home this point.
Yeah.
It specifically says that every antibody is an immunoglobulin,
Right.
but not every immunoglobulin is an antibody.
Exactly.
It seems like that's an important distinction.
It is, yeah.
So what's an example that would help us
Okay.
differentiate the two?
Let's think about law enforcement.
Yeah.
So you've got detectives, right, who are focused on specific cases, much like antibodies target specific antigens.
Right. So they're like the specialists.
Exactly.
They're the experts on a particular threat.
Exactly.
Okay.
And then you have like patrol officers who are more like general immunoglobulins.
Okay.
Who are just, maintaining order, responding to a variety of situations.
Right. So they're not necessarily focused.
Not focused on one specific crime.
On one particular thing.
Right.
Okay. I like that.
Yeah.
That makes sense.
So within the immunoglobulin family, there's a whole spectrum of roles and functions.
Okay.
And each type of immunoglobulin has a unique structure that enables it to carry out its specific tasks.
So speaking of structure, the article talks about this Y shape.
Yes.
That's common to both immunoglobulins and antibodies.
Right.
What's so special about that shape?
That Y shape is absolutely critical for their function.
Okay.
So those two arms of the Y are what actually bind to the antigen.
Okay.
So imagine them like tiny grappling hooks that latch onto the virus or the bacteria and prevent it from doing any harm.
So that shape allows them to neutralize the invaders.
It's all about the shape.
Okay.
And what's really fascinating is that there's this incredible diversity in antigen recognition.
Okay.
So those grappling hooks can come in a vast array of shapes and configurations, allowing our bodies to target, this mind-boggling range of threats.
So we're prepared for pretty much anything.
Well, almost anything.
Almost anything.
But yeah, it's constantly learning and adapting.
Gotcha.
But that's a conversation for later.
Okay.
For now, we'll stick to the basics.
So we've got this amazing diversity of immunoglobulins, all with this Y shape.
Right.
But then the article mentions 5 main classes. IgG, IgA, IgM, IgE, and IgD.
Yes.
What are those? Are those like the different...
You can think of those as like...
branches of the military?
Yeah, like the different branches of the military.
Okay.
Each of these classes plays a distinct role in the immune response.
Gotcha.
So, for instance, IgG is like the veteran squad, making up the bulk of our defenses.
Right.
They're the ones providing long-term immunity after we encounter a pathogen or get vaccinated.
So they're like the long-term memory of the immune system.
Yeah. And they're remarkably effective. But, you know, what about those first few moments when a new threat appears?
Right. Who's responding first?
That would be IgM.
IgM, okay.
It's like the 911 call.
Gotcha.
Quickly deployed at the first sign of trouble.
So they're like the rapid response team.
Exactly.
Yeah.
They might not have the staying power of IgG, but they're crucial for those early stages of infection.
So we've got our veterans, we've got the first responders.
Right.
What about these other immunoglobulins?
Okay, well, let's talk about IgA.
Okay, IgA.
Think of them as the border patrol.
Okay.
They're stationed at all our entry points, like our nose and mouth.
Okay.
Their job is to protect those mucous membranes from invaders trying to, you know...
Sneak in.
Sneak in, exactly.
So they're keeping those pathogens from getting a foothold.
Exactly, yeah. They're the frontline defense force, constantly on guard.
What about IgE?
Okay, IgE.
Now, I know that one's linked to allergies, which seems a little counterintuitive.
Yeah, so IgE is the specialist when it comes to allergic reactions and parasites. They can be a bit of a double-edged sword.
Okay.
Sometimes triggering those, you know, annoying allergy symptoms.
Right, like when they encounter pollen.
Exactly, yeah.
So it's like they're a little overzealous?
You could say that.
Okay.
Yeah, sometimes they overreact.
Okay.
And then finally we have IgD.
IgD.
Now, IgD is still a bit of a mystery.
Oh, really?
Yeah, it's like, you know...
We don't really know what it does.
Yeah, we don't know its exact role yet.
Interesting.
Yeah, but we know it's there.
Okay.
And it's doing something.
So we've got all these different players.
Yeah.
Each with their own specialty.
Right.
All working together.
It's amazing.
It's kind of mind-blowing.
Yeah.
How does our body know which troops to deploy?
That is a fantastic question.
Indoor.
And it gets to the heart of how the immune system learns and adapts.
Yeah.
It's a truly remarkable process.
Okay, let's get into that.
It really comes down to this amazing system of communication and recognition.
Okay.
So it's not just like our immune system is just reacting blindly.
Right.
It actually learns and adapts to the specific threats.
So it's like constantly evolving, getting smarter.
Yeah, think of it like a living database.
Okay.
That's constantly updating itself with information about new pathogens.
Okay.
And the key players in this learning process are these things called B cells.
Okay, B cells, right?
Yeah.
I remember that from the article.
So each B cell carries a unique receptor on its surface, kind of like an antenna, that's tuned to detect a very specific antigen.
So are there all these B cells floating around,
Yeah.
each with like a different receptor,
Exactly.
waiting to encounter their specific match?
Yeah, it's like having a massive library of keys,
Okay.
each one designed to open a specific lock.
Okay, I like that.
And when a new antigen enters the body, it's like trying those keys until you find the one that fits.
Okay, and then what happens?
So when a B cell finds its matching antigen, that's when things get really interesting.
Yeah.
That B cell gets activated. It starts dividing rapidly.
Okay.
And creates clones of itself.
So it's like a chain reaction.
Exactly, amplifying the response to that specific threat.
Okay.
And these activated B cells differentiate into two main types of cells, plasma cells and memory cells.
Okay, and those plasma cells were the antibody factories.
Exactly. So they're like the ammunition factories churning out massive quantities of antibodies that are tailored to neutralize that specific antigen.
So our body's basically creating a targeted weapon to take down this invader.
It's pretty amazing, right?
It's really cool.
And it doesn't stop there.
What else happens?
Some of those activated B cells become memory cells.
Okay, memory cells. All right.
And these memory cells are like the veterans of the immune system.
Okay.
They stick around for years, sometimes even decades.
Wow.
Ready to jump into action.
Okay.
If that same antigen ever shows up again.
So that's how we develop long-term immunity.
That's exactly how it works.
Wow. Okay.
And this memory is what makes vaccines so effective.
Okay, right.
So by introducing a harmless version of an antigen,
yeah,
vaccines essentially give our immune system a training exercise.
Right. So it allows it to build up a defense force.
Gotcha.
Without us having to get sick.
So vaccines are like boot camp.
Yeah, that's a great way to put it.
For our immune system.
Yeah.
Yeah, okay.
But it's not just about fighting off infections.
Right.
This intricate system of antibodies and B cells also plays a role in things like allergies.
Wait, allergies? I thought that was like pollen and stuff.
Well, remember those IgE antibodies we talked about?
Right.
The ones that can sometimes overreact.
Yeah, yeah.
So in the case of allergies, IgE antibodies mistakenly identify a harmless substance.
Okay.
Like pollen.
Right, right.
Or pet dander as a threat.
So it's like a case of mistaken identity.
Exactly.
Okay.
And when they encounter that substance, they trigger this cascade of events that leads to those annoying allergy symptoms.
So it's like they're setting off the alarm.
Exactly.
When there's no real danger.
Yeah, it's like a false alarm.
And in some cases, this immune response can be quite severe, leading to anaphylaxis.
Wow. Okay, so that's serious.
Yeah.
Yeah. Okay, so what about
autoimmune diseases?
Autoimmune diseases.
Did you mention those earlier?
Yeah, so those are a bit more complex.
Okay.
This is where that system that distinguishes between self and non-self.
Right, the friendly fire system.
Exactly. That system goes awry.
Okay.
So in autoimmune diseases, the immune system mistakenly identifies the body's own tissues as foreign invaders.
So it's like it's attacking itself.
That's a good way to put it.
Okay.
And this can lead to a wide range of conditions depending on which tissues are targeted.
Right.
So things like rheumatoid arthritis, lupus, type 1 diabetes, those are all examples of autoimmune diseases.
So this immune system is amazing.
It is.
But also incredibly complex.
Very complex.
There's this fine line between...
You know, fighting off the bad stuff,
yeah,
but not attacking ourselves.
It's a delicate balance.
Yeah.
And scientists are still trying to fully understand how this balance is maintained. It's one of the most intriguing and challenging areas of research in immunology.
It's crazy to think about all this happening inside our bodies all the time.
It's mind-boggling.
Like all these processes orchestrated by this invisible force.
It really is remarkable.
So with all this talk about antibodies and B cells, is there a way to measure the levels of these things?
There is.
In our bodies.
And that's where techniques like ELISA come in.
ELISA, what's that?
So ELISA stands for Enzyme-Linked Immunosorbent Assay.
Okay.
It's a mouthful, I know.
Yeah.
But it's a widely used laboratory test that can detect and quantify specific antibodies or antigens in a sample like blood or serum.
So it's like a diagnostic tool
Exactly.
for the immune system.
Yeah. So ELISA can be used to diagnose a variety of conditions, from infections to allergies to autoimmune diseases.
So by measuring these things, doctors can get a better picture.
Exactly. Gives them a snapshot of what's happening in the immune system at that particular moment.
This is fascinating.
Yeah, it's a really powerful tool.
We've covered so much.
We have.
From just the basic definitions of immunoglobulins and antibodies to like the intricacies of B cells, memory cells, even this ELISA test.
It's a lot to take in.
It is.
But it's all connected.
It is.
It's all part of this incredible story.
Right, of our immune system.
Of the immune system,
And I have a feeling we've only just scratched the surface.
Oh, absolutely.
This.
Yeah, there's so much more to explore.
Right, but maybe we should pause here.
Okay, yeah.
Give our listener a moment.
Yeah, good idea.
To digest everything.
Take a deep breath.
Right.
We'll be back.
Okay.
After a short break.
Sounds good.
To delve deeper into some of the fascinating frontiers of immunology.
Welcome back. So before we kind of went on that little tangent about ELISA, we were talking about how B cells are like these sentinels constantly on the lookout for their specific antigen.
Exactly.
Are there any other cells involved?
Oh, absolutely.
In this whole immune system dance?
Yeah. We can't forget about the T cells.
Okay, T cells.
Yeah, they're like the special forces of the immune system.
Okay.
With a variety of specialized roles.
So we've got B cells and T cells.
We do.
It's like a whole alphabet soup.
Yeah, it is an alphabet soup.
Of defenders in there.
But don't worry, we won't go through the whole alphabet today.
Okay, good.
We'll just focus on the T cells for now.
Okay, perfect.
And how they contribute to this incredible defense network.
All right, so what makes T cells so special?
Well, unlike B cells,
Okay.
which produce antibodies that can directly target and neutralize invaders in the blood, T cells are more involved in cell-to-cell combat. So it's like hand-to-hand combat.
Right.
Rather than long-range attacks.
Okay.
And they have a couple of main ways of doing this.
Okay.
Some T cells, called cytotoxic T cells.
Cytotoxic T cells?
Yeah, they're like assassins.
Okay.
They directly kill infected cells.
Oh, wow.
Preventing the spread of the virus or bacteria.
So they're taking out the infected cells.
Exactly.
Before they can make more.
Yeah, it's a very effective way
of the virus or bacteria
to stop an infection in its tracks.
Okay.
And then you have helper T cells.
Okay, helper T cells.
Now, these are like the generals.
Okay.
They're orchestrating the immune response.
Right.
They release signals that activate other immune cells, including B cells and cytotoxic T cells.
So they're coordinating the whole attack.
Yes, exactly. Making sure everybody's in the right place.
Yeah, they're essential for a strong
Got the right time.
and effective immune response.
Okay, so we've got these T cells.
We do.
B cells, antibodies.
It's
all working together.
Yeah.
It's like a symphony.
Well, it really is.
That's amazing.
And this complexity is what makes the immune system so fascinating.
Yeah.
And so challenging to study.
With all this complexity, how does our body ensure that this powerful system
That's the million-dollar question.
doesn't turn against us?
It all comes down to a process called immune tolerance.
Immune tolerance, what's that?
So during development, our immune system undergoes this rigorous training process to distinguish between self and non-self.
So it's like teaching them.
Yeah, it's like a boot camp.
To recognize friend from foe.
Exactly.
Okay.
And this training happens in specialized organs. Like the thymus.
Yeah, where T cells learn to recognize our own cells and molecules. And any T cells that react too strongly to self are eliminated.
So they're weeded out.
Yeah, they're weeded out.
Okay.
To prevent them from causing harm.
But what if this process goes wrong?
Well, that's when we can develop autoimmune diseases.
Right.
Where the immune system mistakenly attacks.
Right.
Our own tissues.
Okay.
So it's like a case of mistaken identity.
Yeah, on like a grand scale.
On a grand scale, yeah.
Okay.
And so it's a delicate balance, right?
Yeah.
You know, making sure the immune system is powerful enough to fight off real threats.
But not so powerful.
But not so powerful.
That it attacks us.
That it turns against us.
Okay.
And scientists are still trying to fully understand how this delicate balance is maintained.
It's mind-boggling to think about all this happening inside our bodies all the time.
It's pretty incredible.
This invisible defense force.
It really is remarkable.
Doing all this work for us.
Yeah, and the more we learn about the immune system, the more we realize how intricate and elegant it is.
I think our listener has gotten a crash course.
They have.
In immunology today.
Yeah, we've covered a lot of ground.
From the basics to the complexity
to T cells.
Of immune tolerance and everything.
Yeah.
It's been quite a journey.
It has.
So what is the one key message?
Well, I would say
that you want our listener
the immune system
to take away from all of this
is not just a collection of cells and molecules. It's a dynamic and interconnected network. Constantly learning and adapting to protect us from the world around us.
And there's still a lot we don't know.
Oh, absolutely.
But what we do know is amazing.
It's pretty awe-inspiring.
Okay, well, on that note,
I
think that's a good place to end.
I agree.
So, thanks for joining us.
Thanks for having me.
On this journey into the world of immunology.
It's been a pleasure.
And until next time, stay curious.
Yes, absolutely.